Hello everybody, welcome to this presentation about BTFGen. I'm Mauricio, I work as a software engineer at Microsoft and I will do this presentation together with Rafael, that is an open source engineer at Aqua Security. Okay, so let's get started. The problem that we are trying to solve with this presentation, or better with this BTFGen project, is about eBPF portability. We all know that the eBPF is a virtual machine that runs inside the Linux kernel. So we could think that this is possible to just compile our eBPF program and run that in different Linux machines without any problem. But if you are a little bit familiar with eBPF, you know that this is not easy to do because those eBPF programs need to access different kernel structures to get information that is used for tracing or security purposes in general. The problem here is that the layout of those kernel structures is not stable. So it could happen that from one version to the other, the name of a member inside a structure is changed. It could happen that there is a new member introduced at the beginning of the structure, and there are many different cases where the layout of a kernel structure from one version to another could change. Even worse, if we are running the same kernel version, it could happen that we compile the kernel with different configuration flags, and in this case, the layout of those structures is also different. For instance, here we have a very simple BPF program. In this case, we are accessing the PID of the task structure, and when we look at the definition of that structure, we can see that just at the beginning, there is a conditional compilation flag. So according to the value of this flag, the position of the PID member within the structure is going to change. So what it means is that if we compile an eBPF program for a machine that doesn't have this enabled, that eBPF program is not going to work in a machine that has this flag enabled, because the position of this member is going to be different, and then our eBPF program is going to read the information on a wrong position in memory. There is already a solution for this problem. This is called compile once, run everywhere. This has been around since 2018. And this is a mechanism to patch the BPF programs at runtime. So the idea is that we compile the BPF program a single time, and we ship the compile eBPF program. And then on each target machine where we want to run the program, there is a loader library that takes some information about the types of the kernel in a format that is called BTF. More about that in a second. And by using that information, the loader library is able to adjust the instructions on the BPF program to read the members at the right position. All of this is based on something that is called BTF. This stands for BPF Type Format, and this is a metadata that describes the different kernel types. This is an information that is generated when we compile the kernel, and this is exposed to the loader library and in general to the users by using this file. This is important to notice here that this is only available when the kernel was compiled by using this configuration flag. Here we can look at a small piece of BTF. So I only want to look at the definition of the task structure. So if we run that command, we can get some information. For instance, we see that there is a structure that is called task structure. We get some information about the size of the structure. This is the number of members, and then we get information for each of the members present on that structure. Here we have the member that we are interested in. This is the PID member, and this is the piece that is interesting for us. So we get information about what is the offset of that member within the structure. So this is the information that the loader library uses to perform the patching of the BPF program. Right, so far everything is great. By using core, we are able to compile our program in one machine, and we are able to ship that program and run on different machines, and the program is patched before running on those machines. But what is the problem? That this BTF information that is needed by the loader library in order to perform the relocations is not available on all the kernels. So maybe this flag is not enabled, or maybe this is running on an older kernel that even doesn't have this flag available. The good news is that for most of the new versions of the major distributions, this is now enabled. So users that are running a very new kernel version are are all good. There are no problems there, but in this work, we were concentrating in users that are running older versions and for some specific reasons, they can't update to more recent versions of the Linux kernel. So what can we do with those older kernels, right? This is still possible to get the BTF information for those. For instance, there is a project that was created by Rafael and by the Aqua Security folks that is called BTFHub that stores BTF files for different Linux kernel distributions, for different versions of Linux distributions. This is some information that is generated by taking some of the debug packages provided by those distributions. And yeah, we can go to a GitHub repository and we can fetch the file that we need. So the idea there is that all of this is the same. The loader library is just the same, but we have to put some logic somewhere to take the BTF file from BTFHub to download that and to install that into the system. So according to the kernel version that we are running, we take the file, install that in our system, and then we provide that to the loader library, and this can do the work just the same as before. Well, what are the limitations with this approach? Each file is around 5 megabytes big. So what it means for us is that this is not possible to ship a lot of those files together with our eBPF program because it will require a lot of storage. So for instance, for supporting 1000 kernels, we will need something like 5 gigabytes. Of course, this is not feasible. So the alternative there is to download that file from internet at runtime, but of course this is not ideal because we need some time to download the file. And even worse, in many cases, this is not possible to reach an external host to download that file. This is where BTFGen comes into play. So what happens is that in order to perform the relocations, we don't need information about all the types of the kernel. So usually when we write an eBPF program, this eBPF program is accessing some of the members of those structures. We are not trying to access all the members in a given eBPF program. So in order to perform the relocation, we only need the information about the types that our eBPF program is using. So the idea behind BTFGen is to take a full BTF file with all the types of the kernel, describing all the types of the kernel, to take different BPF objects, and then by using BTFGen we are able to generate smaller versions of those BTF files that only contain the types that we need in order to perform the relocation for those programs. So for instance here, as I mentioned before, the source BTF file is around 5 megabytes. We have the information about all the types there, and the generated file, according to the complexity of the BPF programs, could be some kilobytes long. So the advantage in this case is that we can ship those generated files together with our application. So for instance, in some experiments that we did for BCC supporting all something like 1000 kernels only require few megabytes, few extra megabytes. So in this case, this is possible to put the BTF information for many different kernel versions together with our application. So what happens in that case is that at runtime, again, according to our Linux distribution architecture and kernel version that we are running, we extract the specific BTF file for that environment, and we give this to the loader library that performs the patching process as before. And that's it from my side. So I give the word to Rafael that is going to present you a demonstration of how it works.
Thank you, Mauricio. So the idea here is to show one of the projects benefiting from what Mauricio just described. We have like 3 or 4 projects using BTFHub together with BTFGen. The 2 biggest projects are Microsoft's Inspector Gadget and Tracy from Aqua Security. Using Tracy as an example, we have the BTFHub archive in here, and it contains, like Mauricio said, a bunch of BTF files, one to each kernel we would like to support, remembering that these kernel versions here don't have embedded BTF files on them. So that's why we have external BTF files. And then checking how we are compiling tracing and using it. The idea is very simple. every time we generate a eBPF object that supports core and is meant to be portable, we also embed a bunch of BTF files in the final binary. So in our case, it's a Golang binary. And what we're doing is that we are embedding all the BTF files that we have generated with BTFGen in the same binary. And then during execution, we're going to use them, as I'm going to show you in a bit. The scripts that do this are basically getting all the files from BTFHub, and to each of those files, we uncompress the full BTFs, and then we run BPF2, gen, min core BTF, and then we have a full BTF file, and then the file that we are about to generate, and the eBPF object we just compiled. So during the compilation, you're going to see something like this, which is basically running BPF2 and then generating a custom BTF file from this full BTF file for this eBPF object. And if we pick this file is the full 4 or 5 megabyte file, and this one is a very, very small file that is going to be embedded in our final application. And the make file has one option called BTFHub equals to 1, which will embed all the BTF files that we would like to support. And it works a little bit like this. So it compiles the BPF core object. And right after compiling the BPF core object, it synchronizes and it brings all the BTFs I would like to support for all the kernel versions and their architectures I would like to have supported, right? And right after bringing those files, I pick and start generating the smaller BTF files for the object we currently have. So as you can see here, we are supporting Red Hat 8, the versions that did not have BTF file included on it. And then we're supporting a bunch of Ubuntu or Oracle 8 kernels, Ubuntu kernels. And what each line here means is that for each of those BTF files, we are calculating a smaller BTF file base for this object, right? And at the end, if we go to the end, we finally generate the full Golang binary containing all those BTF files embedded on them, right? Like this directive here. Okay, and as you can see, for example, in a kernel that does have all the BTF file, all the BTF information available, you can simply do a paho to this file in here, and you're going to see all the types that your current kernel supports, right? And it's a very long file, right? But when we go to a machine that doesn't have that file available, like for example, an Ubuntu Focal with a kernel 5.4.0-91, this kernel did not have BTF embedded information available. So what we will see now is that if I execute Tracy, it has that available information embedded on it. So it generates a temporary file. And this BTF file here is the BTF file for this kernel, but only the portion needed for running this program, the BPF, the core object for Tracy. So if I do a paho in that file, instead of having all the types available to the kernel, it has only the types needed by the BPF object we're currently running. So as you can see here, it's a small file and it's not complete as well. So it's not as big as the full kernel types, and it has only the types and the fields needed for the BPF program we're currently running. Right, and with that, I give you back the speech. Thank you, Mauricio.
Thank you, Rafael. So in the conclusion, we have that BTFGen can be used to support core on kernels that don't provide BTF information. And we want to be clear here. We know that BTFGen is a temporal solution. So once all the users upgrade the kernels to versions that provide this BTF information, BTFGen won't be needed anymore. But in the meanwhile, you can use that to fill that gap. And finally, those are 2 blog posts in case you want to know more. The first one describes The implementation of BTFGen gives a general overview and also goes into some of the details. And in the second one, explains how this is used by Tracy to solve the lack of BTF information. That's it. Thank you.